everyone see my screen?
Yeah, I can.
Okay, great. Hi, everyone. Thanks for having me here. I want to maybe introduce a bit on how we as a Grab guess ETA in this talk, and please feel free to interrupt me anytime in the talk. So I want this talk to be more interactive. You don't need to wait until the end for the Q&A session. Okay, first thing, I assume like everyone has more or less some experience about a car hailing app. So Grab, basically, we are a day-to-day super app in Southeast Asia. It might be not familiar to everyone in this room what Grab is. Basically, we have several business like car hailing. I think Japan has Uber. I would assume you guys are familiar with Uber. And we are also doing food deliveries. I'm not sure what's equivalent in Japan. If you have Uber Eats, that's more or less the same thing. So back to ETA. ETA is estimate time of arrival we show in the app. So I guess if you open Uber, when you book a car, you can see a number here, 3 minutes, which indicating how long it takes for the car to arriving at you. I had some experience on Uber in Tokyo like 3 years back. I feel the experience was nice, except the price is a bit high. So in today's talk, I want to introduce to the forum here how we calculate the ETA for this screen from our backend. And I will also want to share what's the current status of our ETA calculation. So let's say a driver is actually 4 minutes away from you. Averagely, we can give our customer an ETA of 3 minutes or 5 minutes. So it's quite clear that we cannot give or predict a very accurate ETA. We are still not able to give you 4 minutes, but we are not that far away from the accurate number. Some other states not about the accuracy of the prediction, but more about the system stats. We are doing microservices here in the backend. So this is one of the, so some key services are handling like 30K QPS in the peak hour. QPS is standing for query per second, and it's still growing. And at the same time, we are also always optimizing the queries from other systems like downstream, upstream. But I want to give everyone an overview about our scale. Then I would like to share why we are doing this. Okay, I saw a question. What is, you mean QPS? Is basically query per second is from, let's say the backend service view of point of view, every second, how many requests we receive. So we need to respond with under the short amount of time. So 30,000 is the peak hour. This is the scale we need to handle from the backend service. Why we are doing that? I'm not sure some of you may have some experience on Google Map API. It's widely used across the world. People may ask why you cannot just simply call Google. So we have several motivations back then. So we have some concerns about the quality, because Google Map is performing awesome in most of the world, but in certain regions or countries in Southeast Asia, like Vietnam, Thailand, the quality might not be as good as, let's say, US, Japan, Europe. So that's why we feel we need to build our own technology to predict that. Second is we have a lot of business usage in our car hailing business. So for example, we have two-wheelers. Two-wheelers is basically motorbike. If you have ever been to Southeast Asia, you will see a lot of motorbike driving in the street. is a very common transport tooling for the locals. But in the very beginning, we look into this problem. Google doesn't support that very well. So for us, we need to have an accurate ETA analysis or prediction for those fleets for our customers. So we have to come up with some idea to solve that. Of course, the last thing about the cost, we feel like we can save a lot of cost from a in-house solution. And in terms of impact, ETA is not the final number you can see in the customer screen. It's also a fundamental element for all the other services. So let's say when you book a ride, when you press a button in your app, so our backend system will try to retrieve all the drivers around you, the nearby drivers, and you are not the only passenger who wants a car now, right? So we receive tens of millions of requests every minute. So we need to have an optimization algorithm running there to have the best driver assigned to you. The best might not be the closest, but it's a kind of global optimization in this region. So you will get a driver who will come to you in the next 3 or 4 minutes. And our ETA is a fundamental input to all these systems because they need to understand in the real world how long every car nearby to you takes to approach you. So we are the fundamental engine to provide this information ETA to all the other optimization algorithms to make the right decision. Yeah, and we also save a lot of money for the company by building this system. Okay. So when we understand the problem, this is for system MVP we are building. We are using Go. If you guys are familiar with Go, you can read the source code. It's quite short, it's very easy. So we are an engineer. It only takes us maybe 2 minutes to come up with this MVP. It's a bit funny, but we will just give you the idea that it could be very, very simple. You can predict the number. It could be as simple as we just put a random number from 0 to 5 minutes, and you just return that to the customer. But it doesn't make sense at all if we want an accurate number. But we just want to make everyone understand. It could be very simple, and it purely depends on your accuracy requirements of this value. Then I think after the MVP, if we really zoom into the problem, it could be super complex. So in the following, I will go through the whole system with you from different angles, from sense, memorize, predict, to see how complex it is. So we will start with sense. So for the next 10 minutes, you will be feeling like I'm not talking about ETA, the problem itself, but please be patient. I need to introduce more fundamental elements. We need to make sure they are right first. Then we will talk about how we calculate ETA. So we will talk about sense first. Sense is basically how we sense the real world, and we digitize all of them into our system. So I just list out 3 bullet points here. We need to understand the map. We also need to understand where the driver is. We also want to understand what's the real-time traffic happening in the street now. Let's go through it one by one. Okay, first about map. I want to use one example to highlight how important the accurate map data is, which will impact a lot in our routing and ETA problem. So if you look at this map, and you can see the arrow here, when we debug this issue in our visualization tooling, we realize that we have one missing road over there. The missing part is very small. It's just between 2 streets. The connection in between are missing in this digital map. Then we use this map internally to predict from this origin to this destination how long it takes. So when we do the routing, we realize this is our routing. And the blue one is is where the driver actually drive. It could be totally different. And imagine if your map data is wrong, it's quite impossible you can have all the ETA correct or you have all the routing correct. And it could be totally off with one small missing part. And map data could be a lot of different dimensions. The geometry, whether the road shape is correct or not. It could be traffic rules. For example, this road is one way, you cannot turn left here. And we also have totally different rules for motorbike and motor cars. I would imagine Japan will have similar this kind of restrictions as well. And we have a lot of hyper-local issues we need to tackle. For example, in many cities in Indonesia, they have some traffic rules like odd even car plate number restrictions. So I'm not sure whether it's the same in Japan, but let's say in Jakarta, the capital of Indonesia, in many main roads in the city center, you can only go onto this road if your car plate number ends with odd number or ends with even number. So all these are quite dynamic. You cannot embed all this information into the map data. You need to find a specific customized solution to enable this business scenario, the business requirements. We also have a lot of time-based accessibilities, like only from 4 to 7, you are allowed to go into the street. Other time you're not allowed, so on and so forth. We will also have very, very temporary road closure, like today is the birthday of the king, we need to close this road. So we also need to make sure our system can adapt to this kind of dynamic change. And we also need to make sure all this change can be correctly reflected into our map data. So I will just introduce some method we have used. I may not be able to go to very details or a very comprehensive overview on everything we are doing. I will just pick one or two most important things we feel is quite useful. So we apply several different methodologies like KDE, kernel density estimation, and we also apply different clustering methods, try to infer the map data, for example, the missing row, which didn't exist in our current map data, but they do exist in the real world. You can easily tell from this figure. So as you can see, all the white and gray streets are existing data in our database, in our map data. But if we use our, let's say, driver GPS from their real trajectory, we apply our KDE and clustering methodology, we can extract all these skeleton, all the blue lines. We can detect all these are missing roads. We need to add back into our map data. So imagine there are so many missing roads in our current map database. It's quite impossible that we can give you a correct routing or correct ETA. So we need to, this is the first thing we have enhanced in our fundamental map data. And this example is something we encountered as a very challenging part. So we have very large shopping complex in different capitals or major cities in Southeast Asia, and they have very small roads going through in between, where it makes our KDE and clustering methodology a bit harder to detect everyone. Then we need to choose a lot of hyperparameters, etc. So when we zoom in, and we will find out we have a lot of this and that challenges from different countries and different cities. I hope I didn't go too fast. Everything is fine. Do we have any questions so far? Okay. All right. Looks we are fine. So after we enhance our map data, the second thing we need to understand is where's the driver, right? It's if we don't know where the driver, we cannot tell how long it takes for the driver to approach you. You might ask why we need to do that. Isn't that very obvious? Because nowadays every phone has a GPS sensor, GPS chip within your hardware, it can report where you are. And when you open like your map app, Apple Map, Google Map, you can see a blue dot there, right? This is where you are. But unfortunately, we have to sense where the driver is because several reasons I can show you. So many times, if we just use a GPS reported by either Android or iOS, sometimes when you visualize this on the map, you can see, okay, the car is in the middle of the building, or the car here is in the middle of nowhere. It's not on the road. The road is actually here. Oh, by the way, this is the one of the earlier version of our app. Our current version, our current design of the app is much better. So sorry about that. And because we solved the problem, so if we really want to have a screenshot of that problem, I need to use some previous version to illustrate that. And this is one very interesting case because our running market is in Singapore, but some customer may see the driver is in South Korea if it's not North Korea. Yeah, because it happened because your GPS could be very noisy, and your it could jump, right? And sometimes the jump is still reasonable, and many of our customers can understand. They're very nice one. They can understand the driver is in the building. The driver is somewhere off the street. It's fine, but this is really this went a little bit far, right? So GPS went to another country very far, 10,000 kilometers away, perhaps. So then we find out we really need to resolve that. And some other people, they want to game with systems. They try to come up with an app to fix the GPS. There are so many reasons people want to fix GPS. For example, if they know many people need a car in the train station or in the subway station, but they are literally a bit far away, they can fix their GPS to be as close as possible to a train station. Then when we assign a booking to the driver from the passenger request, we will consider this driver in a prioritized position, right? Because they are closer, but actually they are not. They are very far away. But they took this advantage by faking their GPS. This is also something we try to resolve by looking into all the fundamental sensors. And if we zoom out a bit, you will see sometimes the GPS, the latitude, longitude reported are accurate, but still we are still confused where the driver is. If you zoom in, you can see the example here, right? Because a lot of road networks are super complicated. So you will see a flyover, you will see a tunnel. Then a simple lat long, which gives you the pinpoint of the driver, is not sufficient, because the same lat long can indicate the driver is either on the flyover or on the underground tunnels. Then for us, it's super important to understand where the driver really are driving on, which road segment. So the road segment is kind of a semantic meanings for our system. So lat long itself is not good enough. I hope I illustrate the problem, why we want to solve it clearly. And then I will also introduce a bit on how we solve it. So we have several steps. The first thing is map matching. Map matching basically is nothing but we match the driver location, a sequence of GPS, onto a road network, which is the map data we just discussed. Then we apply different customization and filtering logic onto the system. So this is one illustration of the map matching. Imagine the red square here are the real GPS samples we collected from the mobile phone. They are noisy, as you can see. In this case, our job is to match a sequence of these red dots onto either the green one or the blue one, because in reality, the driver can drive either on the upper road or on the lower road, right? I mean, sometimes it's a very hard problem to tackle, because even, let's say, if I show this visualization to me, I cannot tell where the driver actually. So this is one very extreme case, but many times from a sequence of dots, we can still use some mathematical tools to resolve that. So basically, we model this problem into hidden Markov model. So all the GPS reported are the observations, and we need to use different hidden states to model what's the most likely state, which is the road segment the driver is driving on now. I may not go into very details about the hidden Markov model, but that's a basic idea. And we also need to model different probabilities, right? To map the relationship between the hidden state and the real observations. So basically, we need to figure out the transition probability, the emission probability, etc., to make sure the model we have in theory can really model the observation, the real data we collected from our mobile. We have published, we have a patent, we have a paper discussing how we tackle that. I may not go into very details here, but this theory, this algorithm itself is far away from enough. So in research, to publish paper is enough, right? We have a theory, we solve the real world problem, but if we want to push that into production in industry, we face a series of other challenges as well. For example, we need to match a sequence of driver trajectory onto the road network. The first problem is how long we look back, right? Well, should we look back 1 minute of driver trajectory? Should we look back 10 minutes of driver trajectory? The second thing about sample rate, right? How often we ask our driver's phone to send where they are to us, right? We can sample, we can collect every 1 second, every 5 seconds, every 1 minute. So different sample rate, how it will impact our accuracy, we also need to experiment on. And we also face a lot of challenges that when the driver is in very low speed, or the driver stops in front of the intersection, the GPS has a higher probability to jump. And this will make our matching algorithm a bit harder to infer where you are, because when you're in front of the intersection and you're stopped, we may receive observation of the GPS reported that you are actually in the right side of the road. Then we may predict, okay, you already turned right, but actually you are still stopped. So all these are challenges we faced when we push our system into production. Of course, we need to handle the equal probability, like the illustration I showed in the beginning, that you cannot even tell where the driver is driving on now. And we also need to scale this system into a very large QPS in our microservices architecture. Okay, so now assume we understand the map, we understand where the driver. The last thing we also want to sense is about how the real-time traffic. Okay, so this is the traffic happening. This is a real picture taken in Indonesia. So yeah, this is the traffic we need to handle in our day-to-day life. But actually, the methodology to tackle this is a bit simpler comparing to previous two. One is basically we need to aggregate every driver's speed for each road segment. For example, we have 5 drivers passing by this road segment in last 2 minutes. We have their speed reported, let's say 30 kilometers per hour, 40 kilometers per hour. We just need to aggregate them together. Then we have an understanding on what's the average speed for this road segment. But sometimes the average number is not representative. We also need to understand the P80, P90, etc., etc. So basically, we just need to build a system can handle, can collect the data, and then we can aggregate the data. Then we can apply different statistic values to have an understanding on the real-time traffic. We also have several challenges here, like how long we should aggregate, right? We should aggregate this small road segment, or we should extend to the whole road from from the previous intersection, from previous traffic light, or we also need to handle, should we look at the real-time traffic for last 5 minutes or for the last 10 minutes, etc., etc. All this we need to adjust based on our business requirement, because we collect the traffic data for our future use, for example, for routing, for ETA calculation. So we need to adjust how we do this based on our business or downstream requirements. And we also need to handle a lot of scalability issue, durability issue. Our system about traffic, we have almost 1 million query per second. Yeah, well, we have to, this is scale we need to handle because so many systems running are relying on our traffic data. So we have to have, so million per second, this is the scalability level we need to handle. Another problem we have to solve is how we can evaluate, how we can tell, for example, from our system, we can query, okay, this road segment, this boulevard is 50 kilometers per hour. But how we can tell whether our system gives a correct number, a correct aggregation or not? Because the problem is we don't have ground truth at all. This is another challenge we have to tackle. This is another photo we took from our local team. We understand another challenge from this photo is traffic on the same road segment could be totally different depending on whether you go straight or you turn left. So yeah, I mean, in some cases, in very complex intersection, we also need to differentiate the model we use, the data model we use within our system to differentiate whether you are going forward, going straight, or whether you are turning left. We have some like laggy latency because we cannot know the driver intention whether they will go straight or not, only after they really like go passing this intersection. So we have some latency there from our real data collection and our prediction, but there's another challenge we need to resolve in our system. Okay, so after the sense part, we understand what is going on in the real world. We have the map data, we have the driver location, we have the real-time traffic. Then we also need to use like different database system, engineering, streaming system. This is not from our team. We have different centralized team working with us to solve all these issues. And we are handling terabytes or 10, 20 terabytes level of sensor data we collect every day. So we definitely need another professional team supporting us to handle all. Okay, yeah, finally, let's say we have a very good model on the real world, and we have a system who can scale to store all the data. Finally, we can do the routing prediction and the ETA prediction. First, I will start with routing. Routing, the problem definition is very, very simple. It's just give a route from the source origin to the destination. I'm very sorry, I'm not familiar with the background of the audience in today's talk. So I have to make assumptions that most of you are from CS background, then you have some understanding on graph algorithms. So I will assume you may learn Dijkstra algorithm when you study graph algorithm. Dijkstra is basically very simple shortest path algorithm, shortest path discovery algorithm. If you are familiar with other BFS algorithm, it's more or less similar. We have a very classic algorithm invented 50, 60 years ago. Can we just simply apply that? Yeah, this is an illustration of the Dijkstra. So let's say this is a graph you have. You can just apply the algorithm and get the shortest path. But unfortunately, we cannot just implement a Dijkstra algorithm into our production system, because this is the graph we use in illustration, but this is a graph we have to route in real world. Of course, this is not a real map we have to route on. This is US, but I just want to highlight here to give you a sense the level of complexity in terms of graph data is totally different. If you imagine you want to apply a Dijkstra, or if you want to think of, if you're more familiar with BFS, from the left to the right across the whole US, your laptop may already fail. A server in the data center may also fail because you cannot handle all the search space in your memory. But if you exchange all this data with your hard disk, your customer cannot wait to receive the response from this API. So how we tackle this? Actually, if you think about the problem, it's a very classic trade-off between the pre-processing time and the online query latency. If you think about DB, whenever you write a lot of stuff into the database and you want to boost your query time, you build an index on it, right? Of course, you have certain overhead if you have indexing when you update the data. Similar things apply to the routing problem. What we have done here is we have to pre-process the whole road network, the map data, the graph. We have to make sure the graph is not dense. We have to make the graph into a sparse way, so that basically the sparse graph is a index of the whole original road network. Then when you run this processing in production in your server API, you can only run the algorithm, the graph search algorithm, into the sparse graph. It's basically the same idea as database, right? You run all the query, basically you can check in your index first, which will accelerate like 10x or 100x. Of course, it has a trade-off. Like the downside is it's not trivial to update the map data. It's very similar to the rewrite analysis in database. So, for example, whenever there's a road closure, we need to like close this edge within the graph. It's more complicated. We need to rerun a lot of pre-processing, etc., so we can make sure we can refresh the index, the sparse map in our production system. This is an illustration of how we convert a very complex original map data into a index sparse version. The very basic idea is we try to find out the shortcut, right? So let's say from this source to this node, there is a existing existing path available, and we just want to extract this out with a simple shortcut from A to B, and we have an updated weight over there for this shortcut. And we will do this level by level. So after several iterations, we can convert a very super complex US graph into a very simple sparse graph. Maybe you can see one node for each state. So this is a rough idea we have. But you can imagine, right, if you update one segment here, this shortcut needs to be updated, and all the shortcuts in the above level need to be updated as well. That is not trivial. Let's say after we resolve this scaling problem, the performance problem of the system, another problem we are facing is the routing is basically we need to give you the best route from A to B. What is the best route? I'm not sure how many of you are driving in Tokyo, so I would assume you use a navigation app. Let's say it could be Waze, it could be Google Maps. Many times it will give you, when you start the engine, when you enter the car, you usually put a destination in the app, and sometimes it will give you several suggestions, right? Sometimes it will give you 1, 2, 3. One is the shortest, the second one is the fastest. It could be some other alternative routes to give you. So you can select one of them. So it's always a problem for us because we try to find the best route plan for our drivers. So many times we observe that shortest route is not best. Because maybe this route is shortest, but one segment of it has very bad traffic, has a jam. You certainly want to avoid that. And many times, different drivers are different, right? Some drivers prefer I don't want to have too many turns. You may see some zigzag route plan. Some drivers prefer this kind of route plan if it can give me, it can make me faster. So we also need to understand the segmentation of different drivers, their preference. Of course, you cannot send a survey to the driver, right? So we try to do the analysis based on their historical data, their historical trajectory, to find out, okay, maybe this driver is favor for less traffic light. That driver is favor for fastest, etc., etc. So that is something we try to learn from our driver's trajectory data. Okay, finally, I hope everyone's still with me. The topic of today is how we get ETA. Finally, we are here. We will talk about ETA now. So now the problem definition is very clear. Given a route, what's the expected time of arrival? We solve all the problems we just mentioned, right? We understand the map, we understand where the driver, we understand the real-time traffic, and we have the route as well. We know the route plan from A to B. I should go on street A, then street B, then turn left on street C, etc., etc. So given a sequence of road sequence, how long it takes to go through this path? So this is a problem we need to resolve. As I mentioned in the beginning of this talk, so far we are not very accurate. Let's say the actual is 4 minutes, we can predict it's 3 or 5. Why we are still quite off? Given we already solved all these questions we discussed so far, because we have a lot of noises which cannot be reflected in our system. Because what we are doing in the system is we try to mimic as close as possible to the reality, to the real world, but it's never possible. Like, we cannot be 100% accuracy. So we have a lot of noise on the real-time traffic. We also have a lot of noises on the turn penalty. Turn penalty means if a driver turns left here, even as a green light, how long it takes? Some driver may only take 10 seconds. Some driver is slower, may take 20 seconds. So all this noises is very hard for us to model into our system. Some other real-time incident we cannot catch in our system. Let's say we have an accident here. We have a very temporary road closure because of accident. If we cannot learn that as well as possible, our prediction of ETA will fail. Or of course, we have all the other miscellaneous bias we don't know yet within our system. Then we cannot say, okay, this is noises, we just leave it. So we also apply different methodologies, like we try to learn from our historical data points. We have all the real-time sensors applied nowadays. We also apply different machine learning models. For example, we have all the historical data saying from A to B, how long it takes. We can also learn from that, right? You can imagine on a weekday and weekends, from peak hour to non-peak hour, from A to B, the actual time taken for different drivers are different. But we have tons of data from our business. This is very valuable. We also train our models, try to adjust to cancel all the miscellaneous bias within our system. Okay, I noticed a question. To do something from this. The first question, yes. So basically, the idea of we do the indexing, we try to build an index of the road network is very similar idea comparing to database. When you build an index, basically you want to boost the query time, right? So it's a very, very similar idea for us. We try to build a sparse graph. So when we run a query, let's say we want to run a routing algorithm, we can run the routing algorithm on a sparse graph, which could be 10x or 100x faster if we compare it to if we run on the original graph. So it's a similar idea. If you want to do a query in database, you have to scan the table, is super slow. But if you want, you can run the query in the index is much faster. So this is the idea we borrow from the DB domain. Hope you answer your question. All right. Yeah, I think I almost finished my talk. We have went through how we sense the real world, how we memorize. Sorry, not much, but how we memorize this data, and then how we predict routing and use the routing, how we predict our ETA. And if we're looking forward, we are also thinking different level of city optimization. So for example, for one driver or for one booking from our customer, we can give the driver the fastest, the shortest. But sometimes we also need to think about the high level optimization. For example, we have like several highways within Singapore, but we cannot navigate all the drivers to go to this highway. I mean, if you have heard of all the network flow problem, it's quite similar. We try to minimize that thing, the possibility of that happening. So in our level, because our penetration is quite high, you can assume that maybe 5%, 10%, even more of all the vehicles running in the city are our Grab drivers. So we have a very good representative of what is going on in the ground. So what we are doing is we want to do a city level optimization. We can navigate this driver to this highway, some driver to that highway, so we can balance the traffic. So this is still ongoing work. We also see a lot of like difficulties and challenges there. Yeah, but I think that will be very valuable to our business and to the government. Yeah, I think that's all for my talk. Please feel free to raise questions. Okay, what kind of DB do we use? To be very frank, we don't use any DB at all. So because DB is too slow in many of our use cases, given our scale, we store everything in our memory. So we have to build a distributed layer where we shard different information, different data into different servers within the system. So yeah, so in short, we store everything within the memory. So yeah, everything's within memory because the latency, the round trip time to the DB is not acceptable to our system. We have to answer the question, let's say the ETA question for example, from West Coast to the East Coast of US within 10 milliseconds. So under that service level agreement, we feel like we cannot use any DB. But I'm not a expert in database, and we have done this analysis and benchmarking several years back. Maybe today there are some database available to meet that criteria. That I'm not sure. So feel free, if you have some suggestions, please feel free to let me know. Next question. Rust. Grab. Most of our backend service are written in Golang. Do we have? I'm not sure we have any Golang developer here. We are not a big company yet. We have thousands of R&D, but we try to minimize the investment in developer experience. For example, we have monorepo, we have a lot of toolings for Golang, for our, let's say, linters, compilers, etc., etc. So we try to encourage everyone to use Golang as much as possible. We also have some backend service written in other language. No Rust yet. Because usually it will be a huge investment to build all the toolings for the developers if you want to adopt a new language. So usually it's a comprehensive process whenever the company is considering a new language to bring into our production environment. Okay. You have different versions of sparse graph indexing based on time. Yes and no. So how should I put this? So we have one unified algorithm we have developed to make the sparse graph from the row network. So at one specific time point, we only have one version. However, because the original map data will change over time, right? So you may have different topology, you may have different geometry. Then when you apply the algorithm, you will see different results in terms of sparse graph outcome. The algorithm we use is also no secrets public. If you search CH algorithm, contraction hierarchy, we build our system based on that idea. Of course, we have done a lot of customization for our own purpose, but that is the basic idea. How we extract the sparse graph is more or less the same from CH. So we have a unified okay. Yeah, we have a unified version, but over time, because of original data change, we have a different sparse version. How about where this? Okay, it depends. If you are asking about let's say Gracia data or the very cold storage data, and we only need to apply analytical purpose onto them, then most of the data are storing in our data lake. So we run most of our services in AWS cloud. So if you are familiar with AWS, we store most of them in the cold storage, in the blob storage like S3 and others. So then, but we have the data could be formatted in different for different requirements. For example, it could be Parquet, it could be Avro, depends on how you want to query it. Then we have different query engine building on the data. So for our analytical people, they can run a very simple SQL command. Then our query engine can convert this into either a Spark job or whatever to retrieve data from different Avro or Parquet underlying data and return the result to the analytical people. And we also build our BI based on this. Okay. I hope I answered your question. You mentioned about hidden Markov models, maybe with sensor regression. Can you model your model in data? Okay, so yeah, basically, if you think about hidden Markov model, the observation is where the driver are from our GPS prop. Let's say the let long. The hidden state, we just use the row segment surrounding this let long. So if you imagine we have a some data structure like Archie, given a let long, because let's assume we have all the spatial indexing already, like within the Archie, that given a let long, you use the Archie to retrieve all the nearby segments. Then every segment is a hidden state. Then how you can connect the segment with a let long, we simply project, do a perpetual projection from the let long to the segment. So you have a projection point in the segment, and the projection point has its own let long. So that let long is a hidden, the equivalent hidden state when we apply the forward coding and backward vector B. Basically, what we need to infer is the emission probability, which is how far the distance between the original GPS, let alone, and the projection, let alone. And we also have the transition probability, which is from this observation to the next observation, because it's Markov model, right? If we just look at the next one or the previous one, what's the straight line distance from that let alone to this let alone, and what's within the hidden space, what's the driving distance across each previous row segment to the next row segment. Of course, you need to have different permutation to get all the transition probability, because you need all the likelihood from segment A to segment B, segment A to segment C, etc., and vice versa, right? After you have all this probability, you can do the encoding forward and do the vector B decoding afterward to get the most likely path from the trajectory. If you are interested, there's so we have done a lot of customization and optimization, but all the original idea was very, very basic. Sorry, let me turn on my light. All the original idea is very basic. You can search map matching, hidden Markov model map matching in Google Scholar. You can find a research paper from Microsoft Research in 2009 from John Kroom. They give a very good explanation and illustration on how they model the map matching problem using hidden Markov model. A lot of following the study has been done based on this research. Our work is also similar. We also do a lot of further work based on a very similar idea. Okay. Yeah. I'm not sure whether we are running out of time or we have further question from the when. Yeah, you're welcome.
Yeah, hi, I'm here. Let's see. Yeah, let's see whether we have further questions. And thanks a lot for giving the talk.